This metal cylinder contains enough energy to produce fire for weeks. But here's the strange part. Most of what's inside isn't actually gas, it's liquid. And somehow, that liquid instantly transforms back into gas the moment you turn a small valve. Which raises a much bigger question. Where does LPG actually come from? The process begins deep underground, inside massive hydrocarbon reservoirs buried beneath layers of rock formed millions of years ago. But extracting LPG is far more complicated than most people realize, because what comes out of the ground isn't ready to use fuel. Before it can ever reach your kitchen, it has to be extracted from deep underground, then pass through giant industrial systems designed to isolate, transform, and stabilize one of the most volatile fuels used in everyday life. And somehow, all of that ends up inside this small metal cylinder. But how does a gas become liquid? Why the flame is blue? Why doesn't the cylinder explode in extreme heat? How this thing can turn in a bomb? And what actually happens inside those massive refinery systems before LPG reaches your home? Today, we're following the complete journey of LPG, from deep underground to the fire on your stove. If you haven't subscribed to Revalix, do subscribe for upcoming interesting videos. Let's start at the beginning. LPG stands for Liquefied Petroleum Gas, but that name barely hints at what it really is. At its core, LPG is a mixture of two specific hydrocarbon gases, propane and butane. Both are members of the alkane family, chains of carbon and hydrogen atoms. But where does LPG actually originate? This is where the story gets interesting, because LPG doesn't come from one place. It comes from two completely different industrial processes, both happening at enormous scale all around the world right now. The first source is natural gas processing. Deep underground, trapped in porous rock formations, are vast reservoirs of natural gas, mostly methane, but mixed with heavier hydrocarbon compounds, including propane, butane, and others. When this gas is extracted and brought to the surface, it's far from ready to use. It's a complex cocktail of gases, water vapor, carbon dioxide, hydrogen sulfide, and other impurities that would corrode pipelines, ruin equipment, and make combustion dangerously unpredictable. So before natural gas can be shipped through pipelines to homes and power plants, it goes through a processing plant, a facility that strips away everything that isn't methane. And in that process, the propane and butane are separated out, collected, purified, and those become LPG. The second source is even larger in scale, crude oil refineries. When crude oil is pumped out of the ground, it is one of the most complex natural substances on Earth. A dark, viscous liquid containing hundreds of different hydrocarbon compounds, each with its own boiling point, density, and energy content. To make it useful, refineries must separate these compounds, and the primary tool for doing that is something called the atmospheric distillation column, a towering steel vessel that can stand over 60 meters tall. Here's how it works. Crude oil is heated to extremely high temperatures, around 350 to 400 degrees Celsius, and fed into the base of the distillation column as a mixture of vapor and liquid. As this mixture rises through the column, it cools gradually, and at each level, different compounds reach their boiling point and condense back into liquid, collecting on trays spaced throughout the tower. The heaviest products, bitumen, heavy fuel oil, stay near the bottom. Higher up, you get diesel, then kerosene, then gasoline. And at the very top of the column, where temperatures are lowest and the compounds are lightest, that's where LPG is collected. LPG is essentially the lightest fraction of crude oil refining. Propane and butane, along with a small amount of other light gases, rise to the top of the column and are drawn off as vapor. But here's what happens next that most people never think about, because collecting it is only the beginning. At this point in the process, propane and butane exist as gases, warm, light, and completely impractical to store or transport at scale. A single tanker truck filled with gas at atmospheric pressure would carry almost nothing useful. The economics simply don't work. So engineers do something elegant. They compress it. And here's what makes propane and butane uniquely suited for this, because most gases require extreme cold or crushing pressure to become liquid. Nitrogen, oxygen, the air you're breathing right now, none of them liquefy under ordinary conditions. But propane and butane are different. Propane turns liquid at around 8 times atmospheric pressure, butane at even less. That single physical property is what makes LPG possible at all, and it's what makes everything that follows work. Imagine a room full of gas molecules, constantly moving, bouncing off each other and the walls, occupying every bit of space available. Now imagine squeezing that room smaller and smaller. The molecules get closer, they collide more often. The pressure climbs, and at a certain point, a critical threshold that depends on the specific gas and its temperature, the forces between molecules overcome the energy pushing them apart, and they lock together. The gas becomes liquid. What makes this remarkable is the energy density transformation. 1 liter of liquid LPG, when it vaporizes, expands into roughly 250 liters of gas. You are storing 250 times the volume in that same space. That's why a cylinder that seems small enough to carry with one hand can fuel a family kitchen for weeks. The gas is compressed in stages, industrial compressors working in sequence, cooling the gas between stages to prevent excessive heat buildup. By the time it reaches the storage stage, it is dense, liquid, and carrying an extraordinary amount of chemical energy in a remarkably small package. Now it has to get from the refinery or processing plant to you. And this is where the engineering becomes genuinely fascinating. LPG is transported through the world via 3 main routes: pipelines, specialized tanker ships, and road tankers. Large pipelines carry LPG between facilities, pressurized to keep the contents liquid throughout the journey. For international trade, giant vessels called LPG carriers transport the liquid cargo across oceans in pressurized or refrigerated tanks, some of them holding tens of thousands of cubic meters. And then, at the local level, road tankers deliver it to distribution centers, where it's filled into the cylinders and tanks you see every day. Those cylinders are more sophisticated than they appear. They're designed to handle internal pressures far above normal operating conditions, typically rated for pressures well beyond what LPG generates even on the hottest days. They're built from high-strength steel, tested rigorously before use, and fitted with pressure relief valves that open automatically if pressure ever climbs dangerously high, venting gas safely rather than allowing the vessel to fail. And here's why that matters. On a very hot day, the pressure inside an LPG cylinder can climb significantly. But the cylinder isn't filled to maximum capacity. There's always a vapor space above the liquid, a buffer zone that gives the expanding liquid somewhere to go. The pressure relief valve is the last line of defense. Together, these systems make LPG cylinders remarkably safe under normal conditions. What happens next, though, when that cylinder reaches your kitchen, is something almost no one has ever stopped to visualize. You turn the knob, and in that moment, the valve opens a pathway from the high-pressure liquid inside the cylinder to the low-pressure atmosphere outside. Instantly, the pressure drops, and the liquid, which was only liquid because of that pressure, begins to vaporize. It flashes back into gas right at the valve, flowing out through the regulator, through the pipe, to the burner. The regulator attached to the cylinder top is a critical piece of engineering. Its job is to take the variable pressure inside the cylinder, which changes depending on temperature and how full the cylinder is, and reduce it to a consistent, safe working pressure for the appliance. Without it, the gas flow would be unpredictable, dangerous, and impossible to control. At the burner, the gas mixes with air in precisely controlled proportions, and when ignited, whether by a spark or a flame, combustion begins. Propane and butane react with oxygen in a rapid, highly exothermic reaction. Carbon and hydrogen atoms break their bonds with each other and form new bonds with oxygen, releasing energy as heat and light. The products are carbon dioxide and water vapor, and when the mixture is correct, that combustion produces the characteristic blue flame, the visual signature of complete, efficient burning. That blue color isn't just aesthetic, it tells you something important. An orange or yellow flame means incomplete combustion, carbon particles glowing as they fail to fully oxidize. Blue means the chemistry is working perfectly, extracting maximum energy from every molecule of fuel. But here is where the story takes a darker turn. Because everything that makes LPG so useful also makes it genuinely dangerous if something goes wrong. LPG is highly flammable. Its ignition threshold is low. And here's the detail that changes everything. Unlike natural gas, which is lighter than air and drifts upward when it escapes, LPG is heavier than air. It doesn't rise. It sinks. It hugs the floor, flows into basements, pools and drains, and low corners, completely invisible, completely silent, slowly building in concentration until it finds what it's looking for. A pilot light, a thermostat clicking on, a light switch, a single spark. When that moment comes, the result isn't a slow burn. It's a deflagration, a wave of explosive combustion that can tear through a building in less time than it takes to blink. And here's what makes that even more unsettling. In its pure, unprocessed form, LPG has no smell, no color, no sound, nothing your senses can detect. It could be filling the room you're standing in right now, and you would have no idea. Which is why, before a single cylinder ever leaves a filling plant, engineers inject a compound called ethyl mercaptan into the gas. This chemical is almost offensively detectable. That sharp, sulfurous odor your brain immediately flags as danger. And it's present in concentrations so small they're measured in parts per million, yet still register clearly to the human nose long before the gas reaches anywhere near an ignitable level. It is one of the simplest ideas in industrial safety, and it may be one of the most lives saved by a single engineering decision in history. And yet, despite these risks, LPG remains one of the cleaner fossil fuels available to humanity today. When propane or butane combust completely, they produce carbon dioxide and water, no sulfur dioxide, virtually no particulates. Compare that to coal, which releases sulfur compounds, nitrogen oxides, heavy metals, and fine particles that penetrate deep into human lungs, or wood burning, which fills the air with carcinogenic compounds and black carbon. Even gasoline combustion produces more harmful emissions per unit of energy than LPG. In parts of the world where the alternative is cooking over open wood fires or burning coal briquettes in unventilated kitchens, the switch to LPG has had measurable, documented impacts on respiratory health. It has reduced deforestation. It has improved air quality inside homes where pollution levels were previously reaching catastrophic concentrations. LPG is not a final destination. It is still a fossil fuel, still releasing carbon dioxide, still contributing to the broader challenge of climate change. But as a transitional fuel, bridging the gap between the most polluting energy sources and the clean alternatives still being scaled, it has played a role that its critics often underestimate. So the next time you see that metal cylinder, standing quietly in a corner, chained to a wall, sitting under a grill, think about what it actually contains.